Okay, so here we've got a question about a dam and having 3 leaks, which are evenly spaced, and basically water shoots out. And so you can see that if water shoots out, it will fall under gravity, which makes this a projectile motion question. And so we'll be looking at things from a projectile motion point of view. And so let's take a look at what the question says. You have a dam wall over here, 4D units high, 1, 2, 3, 4. Small leaks occur at 3 evenly spaced intervals, 3D, 2D, and 1D units from the water level. So 1, 2, 3, those 3 leaks. Now, following the question carefully, it says using axes as shown. So here's your x-axis, here's your y-axis. In other words, 0, 0 is here. Show that the parametric equations for the water leak from water leak 1 are x equals vt and y equals 3d minus half gt squared. Well, I haven't really defined what v is, but I think it should be pretty clear that that would be, well, velocity, but they should have really defined that in the question. And you should expect an proper exam paper would do that to tell you if they use a letter what that means. And part 2 very similarly asks you to find the parametric equation for leaks 2 and 3. And so 1 and 2 are quite similar. We'll do that very shortly. And then there's a few questions after that we'll look at afterwards. So let's start by getting our own diagram. Okay, so you were told that this is the x-axis and this is the y-axis. You have water here on the left. You have leak 1, leak 2, leak 3. You know it's projectile motion, so part 1 and part 2 should be quite easy. So we know for projectile motion, we're assuming that x double dot equals 0 and y double dot equals negative g. Because it's a leak, we would assume that your angle of projection is 0 degrees. You're just projecting horizontally at initial velocity equals v. So we would say that, I mean, they didn't really say if the velocity was the same for all of them, but let's assume it is for now, given the question didn't really say much. So that means at t equals 0, we would say x dot equals capital V. Okay, y dot equals 0 because you're projecting horizontally. And for leak 1, x must equal 0 and y must equal d. So leak 1. And then we do, I guess, the parametric equations. So we would, in an exam, if they ask, we would show full working. So x dot would equal the integral of 0 with respect to t. Well, it's the integral of x double dot, which is 0, which is just a constant. We will then need to determine what this constant was. Sub t equals 0, x dot equals v. So we get, well, x capital V equals k, and therefore x dot equals k. Once you have that, to get x, that would be the integral of x dot with respect to t, which is the integral of k with respect to t, which is kt plus c. You would then need to sub t equals 0, x equals 0. So 0 equals 0 plus c, so c equals 0. So therefore, x must equal your v times t because k equals v. And that's how you prove it for x. All quite straightforward. We'll do the same thing for y. So you've got y double dot equals negative g. So y dot would equal the integral of y double dot with respect to t, which is the integral of negative g with respect to t, which is negative gt plus c. You would substitute the fact that at t equals 0, y dot equals 0, meaning 0 equals 0 plus c, so c equals 0. That means y dot equals negative gt. Then you would say y must equal the integral of y dot with respect to t, which is negative gt, which is negative half gt squared plus c. You would sub at t equals 0, y equals d, as we mentioned up here. All the way up here. That gives you d must equal 0 plus c, so c must equal d, meaning y equals negative half gt squared plus d. Okay, so that means that would be the case for that one, but we have actually labeled them incorrectly, unfortunately. Because the question has actually labeled it from top down. So leak 1, leak 2, leak 3. So regardless, that we would have done the same sort of procedure. Okay, we did it from the wrong leak. Okay, so what we would basically do if it had been leak 2, we would let everything would have been the same. X would have equals 0, y equals 2d, and for leak 3, we have x equals 0 and y equals 3d. If you had followed the same steps for leak 3, you should get, for leak 1, I should say, you should have got x equals vd, which is exactly what we got, and y must equals 3d minus half gt squared. You would recognize that the only difference between what they got and what we got was the y we subbed in. And that's part 1. For an exam, if they had asked you to do it for part 1, you don't need to do all the work again for part 2. You can just essentially work out that x here, we're assuming the initial velocity is the same. It's not really given in the question, which is slightly a little bit concerning. We're not sure if the initial velocity is the same for all 3, but let's say they are. That means that would be 2d minus a half gt squared, and this would be d minus a half gt squared. Okay. So let's now do part 3. What does part 3 ask us to show? Show that the jets of water from leak 1 and 3 reach the ground level at the same point, given that the velocity of the water issuing from a tank from a leak is v squared equals kh, where h is the height of the water issuing above the leak and k is a constant. Right. So we can let v be the velocity, but the v is not constant, as we were saying. But now we actually have this situation where v squared equals kh. So you want to show that this and this reach the ground at the same point, horizontally, given the relationship. So we'll need our expressions here. Notice that the x coordinates are the same, but they've got a different v. And the y for leak 1 is 3d minus a half gt squared. And for the third one is d minus a half gt squared. And we have the expression v squared equals kh. So at a particular time t, so let t equals capital T when let's call it, let's call T1 for when T1 lands on the ground. And let T equals T3 for when T3 lands on the ground, because we don't know if it's the same time or not. So basically, how do we find T1? Well, T1 is when let y equals 0, then in for L1, for leak 1, and basically solve for T. So in other words, we're saying 0 must equal 3d minus a half g T1 squared. So that means half g T1 squared equals 3d. T1 squared equals 6d over g. So T1 must equal the square root of 6d over g. Okay. So we've worked out how long it takes for the droplet to hit the ground. And we can do something very similarly for T3. You let y equal 0 for L3, solve for T. So we're saying 0 must equal d minus a half g T3 squared. So half g T3 squared equals d. T3 squared must equal 2d over g. So T3 must equal the square root of 2d over g. So we've got some important results that might be helpful there. Now we're going to need to use those times to find the range and hope that they're the same. And that means we now need to involve our x parts now. The y parts are done. They've done their job. We now need to use the v squared equals kh. Remembering what h is the height of the water above the leak. Pay attention to that. Which kind of makes sense, right? The more water there is above the leak, the more is pushing down. Okay. And keep in mind that this water is 4D units high. So 1, 2, 3, 4. I mean, I guess the water should be drawn a little bit higher over there. The water is 4 units high. So you can see for leak 1, H is just this water, D. And for leak 3, it's 3D. So let's now keep our results and get rid of this part. Okay, so we've got that. Now we've got leak 1. We know that H here is D. We know we've got leak 3. We know that H here is 3D. So in other words, V squared V3 squared equals 3KD. V1 squared equals KD. So V1 must equal the square root of KD, and V3 must equal the square root of 3KD. We would then need to find, I guess, the horizontal range. So x1 would equal v1 times t1, which is root kd, times root 6d over g. Well, that's, I guess, square root of 6kd squared over g. x3, how far the third one goes across, would be, well, v3 times t3, which is the square root of 3kd times the square root of 2d over g, which is the square root of 6kd squared over g, which we'll notice is equal to x1. So at this point, having worked out independently where the first one's going to land and when the third one's going to land, and they're equal, therefore, because they are equal, right? Then with all the equations above, then the two leaks will land at the same position, horizontal. So they've taken different times to land, but they've also gone across at different velocities. And the result of that is they both land this many units away from the origin, across to the right. Now they want you to find the velocity of impact of the water from leak 2 in terms of G, K, and D. Okay. So remember, you want to find the velocity of impact. Then whenever you want to find the velocity of impact, you basically do it in a particular way. You just need to find typically when you're using parametric equations, you just basically find the x dot at that point, the y dot at that point, and then add them together. If you had a Cartesian equation, you might use the derivative, but in this case, we're using parametric equations. So let's do that. So we would firstly start off with our leak 2. Well, what do we know about our leak 2? We know that x equals vt and y must equal 2d minus a half gt squared. We know x dot equals v2 and y dot must equal negative gt. Okay, so we know that at landing, so when t equals t2, this call it landing, then y equals 0. So we need to find when it lands, right? So when it lands, let's solve for that. So that means 0 must equal 2d minus a half gt squared, or gt2 squared, which means half gt2 squared equals 2d, which means t2 squared, of course, is 4d over g. So t2 must equal 2 root d over g. So this is the time when the leak lands. Here. So at that point, leak 2, it lands there. Well, we need to use our relationship, v squared equals kh. Now, in the case of leak 2, it's got 2d below it, and therefore 2d above it. So h must equal 2d. So this must equal 2dk. So v must equal the square root of 2dk. v2 in particular. Okay, so that means we know x dot because we've already just worked out what it is here. So we'll write that in there. But we actually need y dot. And so what's important is at t equals t2, x dot equals square root of 2dk because it's constant for any time. But y dot, you need to actually find the velocity of the vertical velocity at that time. So that means it's negative g times t2, and that's going to be negative g times the square root of d over g times 2. So it's going to be negative 2 times the square root of gd, because you can just multiply this. I'll write it bit nicer. So we'll keep the negative. G goes inside to be G squared, so it's G squared over G, which is just G. And so that's what we have. So what we're really saying at this point is we've got at t equals t2, you've got that is square root of 2dk, that's the x dot, going across. You've got the y dot going down, and that's going to equal negative 2 root gd. And they're asking you to find the velocity. And so all you really need to do here is, well, basically Pythagoras' theorem. So therefore, if we call that v, v squared must equal x dot squared plus y dot squared, which is 2dk plus 4gd. So v must equal the square root of 2dk plus 4gd. Now the question didn't ask for the direction. Technically in physics, the velocity includes the direction, which we could find. And sometimes the maths would ask you to find that as well, but they would, I don't think you need to for this question, because they would usually ask you the angle of impact and so forth. But let's just say that they did ask you to find it. You want to find that angle theta. Then you would basically just do that by using inverse tan of the absolute value. So in this case, theta, which I don't think you need for this question, would be the inverse tan of 2 root gd all over root 2 dk. And you can simplify that a little bit. And assuming you had actual values for g and k, then you could work out the angle below the horizontal. And that's how you'll do that part of the question. The last part of this question asks us about a leak occurs at a distance L units above the ground, so somewhere L. Show that it hits the ground at a maximum distance from the dam if L equals 2d. So in other words, you now want to find some leak somewhere, and you want to find when the range is maximized. Okay, so we'll now need to generalize this. So we understand from the work, so for your leak in general, we know that at t equals 0, x equals 0, and your y must equal L units above the ground, which varies. This L varies. Which then means, using part 1 and 2, essentially you've got x equals bt, and y must equal L minus a half gt squared. Now we should also note as well that v squared equals kh, where h is the amount of water from the ground and L is distance above the ground. So h must equal 4d minus L, because, I mean, if you think about it, you've got your 4d. This is the ground, and this is somewhere L. And so h is this part, the part above, which is 4d minus L. So in other words, now that we've got that, that means v squared must equal k times 4d minus L. So we could write it here already, but v must equal the square root of k times 4d minus L. Okay, times T. So we want to find the range. We want to find so basically, like we want to maximize the range and show that range is maximized when L equals 2D. And basically your steps involved here would be one, to firstly find an expression for range, which is what we're working towards here in terms of L. And then two, once you have that, essentially maximize that expression. Which may or may not involve calculus. We'll see, depending on what the expression is, but it may involve calculus. So we'll kind of basically do things we've done before with leaks 1, 2, and 3, but this time in general. So that's basically our steps, all right? So we'll need to firstly find our time. So we'll need to let y equal 0. And t equals your t to hit the ground. So that means we'll need to solve for t. So basically we'll get L minus a half gt squared equals 0. Half gt squared equals L. So you've got tg squared equals 2 times L over g. So tg must equal the square root of 2L over g. Okay. So we've found when it hits the ground. Now, of course, the range will equal x at that time, which of course is, well, we've already got it mostly written up there. It's the velocity, which we've already worked out, times the time, which we have also worked out. So that's just going to be, I guess, 2L K 4D minus L over G. Okay. So a lot of letters there, but nothing too difficult for the moment. So at this point in time, we've got the range equals the square root of 2KL 4D minus, so for 2KL 4D minus L over G. Now, we could obviously try to maximize that, and we will, but just to be clear, the range is the square root of something. Now, to maximize range, when you've got a square root, it's also, assuming that this is positive, which it is, because the square root of is always positive, it's also equivalent to maximizing range squared. I mean, the bigger your range, the bigger the square. There's no negatives to worry about here. So let's make it easy for ourselves. R squared, just get rid of the square root, 2KL 4D minus L over G. Maximize this, you get the same result, except nicer algebra. And as always, remember what your variable is. Remember K, D, and G are constants in this question. K relates to the velocity. You're not told what it is, but it's a constant. D is the sort of set height of the dam, 1/4 of the height of the dam. That's a constant. G is, well, acceleration due to gravity, again a constant, but L is the variable. It's the only variable. So keeping that in mind, we can take out the constants. That's not really a concern. You've got L times 4D minus L, which we could, it's up to you how you want to do this. You could use the product rule. I will consider it in terms of like a quadratic. And then again, it's up to you how you want to do this now. I'm thinking about it like a quadratic. I have the option of using calculus and taking the first derivative and letting that equal 0. But I will note that r squared is a quadratic with a negative a, concave down. So therefore, it has a maximum at its vertex. It has a maximum at its vertex. I could use calculus to prove that. You don't have to though, because it literally is a quadratic, right? It's constants. It's just in terms of L, you've got L squared with a negative. So it's a concave down parabola. So you know it's going to look something like this. You could use, although you could use calculus to do it, you could use completeness squared to do it, you could use all sorts of ways to do it, but you should know from a theory that the max occurs at L being our x value here equals negative b over 2a. Well, b is 4d, a is negative 1, so that's going to be negative 4d over negative 2, which is 2d. This is just your quadratic theory from year 10, which you're free to use. If you feel like using first derivative equals 0 and then proving second derivative is negative, that's fine as well. It's not really necessary for a quadratic, but feel free to do that. But at this point in time, we have shown that the L equals 2D gives you a maximum. And that's what the question asks for. It asks you to show that it hits the ground at a maximum distance if L equals 2D, and we have shown that. The range is, well, r squared, and therefore range is maximized when L equals 2D, and therefore the maximum distance occurs when L equals 2D as required. And that's how you do the question.